Okay, folks, the show is back on the air. Just give me some feedback as to the speed before. Were we able to follow along? Okay, folks, how was the speed of the presentation before? Okay, we ready to get started? Okay, folks, I need to know if you can hear me there. Okay, folks, last call. If I don't get any answers, I'll shut down. Is anybody there? Can we get started? Ah, okay. Something's wrong with the chat. I see somebody sent me a message. Okay, so let's see if I can fix that. If not, I'll just start. All right, it looks as though looks like the chat is working. Very good, very good. Okay, are we all back? That was 5 minutes wasted. Yeah, I think it's working. I see your... Yeah, there we go. All right. Yeah, good thinking there. Let's see, who was that? Kaiser. Good for you. All right. Let's get started. All right. So what we could do, and what we're not going to do, is to use the limit definition for all the trigonometric functions, because each of these functions can all find their way back to sine x. All right, so the question is how can cos x find its way back to sine x? Well, hopefully we haven't forgotten all those great trig identities that we learned in the last course. All right, and there's a bunch of identities that actually relate cos x to sine x. We can use any one of them. I'm going to use the one that I would say is the easiest of them all. All right, is we can rewrite cos x as sine of pi over 2 minus x. All right. So how can we find this derivative? Well, we know the derivative of sine x, and hey, we can use the good old chain rule to now determine the derivative of cos x. So this now becomes our inside function, our u. So how does let's recall how the chain rule works. So first we take the derivative of the outside function, and then we multiply that by the derivative of the inside function. But what is the derivative of sine u? Well, we just determined that. It's cos u. So in other words, cos of pi over 2 minus x. And then we multiply that by the derivative of u with respect to x. And of course, the derivative of pi over 2 is just 0, and the derivative of negative x is just negative 1. All right, so we're left with here negative. And again, you go back to your identity sheet, and you realize that cos of pi over 2 minus x is just equal to sine x. And so lo and behold, what do we have? We have that the derivative of cos x is equal to negative sine x. So maybe not quite as nice as the other way around. We do have this negative sign that hangs around, but still quite nice. All right, and in fact, if we again take a look at the derivative of cos x, let's open this up. Okay, and you can even do this by hand. So let's animate, or let's trace the point which represents the derivative of the function. And I don't think this is going to be a big surprise that as we move the points along cos x, we end up with another sinusoidal function, and in particular, we end up with exactly negative sine x. Okay. So it follows the same type of pattern as we saw when we were finding the derivative of sine x. All right, so we proved it, and we even have some a nice graphical justification for it. All right, but from now, at this point, we can now find all these other derivatives, because what's the derivative of tan x? Well, it's just going to write it as the derivative of cos x over sine x over cos x. All right, and then here, what's the derivative of cosecant? Well, it's just the derivative of 1 over sine. All right, except you're not going to write it as the derivative of 1 over sine. You're going to write it as the derivative of sine x to the negative 1, so that you can use the chain rule again. Okay, now you got to be careful here when you write this, because you can't write sine negative 1 of x, because that represents the inverse function. You have to put the negative 1 exponent over the whole expression to represent the reciprocal. Okay, this is going to be equal to the derivative of cos x to the negative 1. And easiest way to find this one here is to take the derivative of, instead of 1 over tan x, probably easier to just take cos x over sine x. So I'm not going to do all of these. I'll do another 2. Okay, so I'll do tan x and secant x, and I think you'll see in a second why I chose to do these 2, and you'll see the derivatives for the remaining 2 you can do on your own, and they're pretty similar. All right, so let's apply the quotient rule here. So derivative of sine x is cos x times the denominator function, which is cos x. All right, so next we subtract the numerator function, sine x, times the derivative of the denominator, and we just found that the derivative of cos x is negative sine x, and all over the square of the denominator. All right, nice and easy, cos squared x, and hey, what's this going to give us? Plus sine squared x. This is looking really good, all over cos squared x, and of course cos squared plus sine squared is equal to 1. All right, and there's our derivative. But in fact, we can do one better, and we can write this as secant squared x. All right, so there's our derivative tangent. Okay, any questions before I move on to doing derivative of secant? Okay, doesn't look like there's any questions. Very good. So let's do the derivative of secant. Okay, and so again, while you could write it as 1 over cos and use the quotient rule, much more efficient to write it as cos x to the negative 1 and use the chain rule. All right, so here u is going to be our cos x. So first we take the derivative of the exterior function, which is u to the negative 1, which of course is negative 1 times u to the negative 2. Okay, and then we multiply by the derivative of u, and the derivative of cos x is negative sine x. All right, and so what we have, well, the negatives, they just cancel each other out, and we're left with sine x over cos squared x, which is a perfectly good derivative, but this is not normally how we represent it. So what we do is we're going to split this up into 2 fractions, a product of 2 fractions, and we're going to write this as 1 over cos x, okay, times sine x over cos x, and so that means we can rewrite this as secant of x times tangent of x. Okay, and the reason why we do this is because we see some really nice patterns. First of all, the secant repeats itself and then multiplies tangent. But hey, remember there was a relationship already between tangent and secant. The derivative of tangent was secant squared. Okay, so we see here that this helps us hopefully to memorize these derivatives. Now, if you do cosecant and cotangent, you're going to see that something very similar happens. Okay, there's a little bonus that's going to show up. Okay, but you're going to get a very similar relationship between cosecant and cotangent. All right, but now what we have is the basic derivatives of trigonometric functions, and because we have the chain rule, we can also find any combination involving trigonometric functions, whether it's the sine, cosine, or tangent of some more complex input, or if the trigonometric function is part of some larger composite function. All right. But again, just from the beauty of math perspective, okay, I would like to remind you that this whole thing came down to figuring out this one limit. This one limit led to all the other stuff that came about. Okay, so at this point here, if there's any questions about okay, and if you want to do these, you should be doing these examples. You can check the video at the very end of the video. If you want to see how these are done, you can just scroll to the end of part 2. So, are there any questions? And are there any questions about any of the other stuff? Don't forget there's the homework sheet having to do with the position, velocity, and acceleration. So I'm up for any questions. Let me know. Okay, so Sydney, are you talking about on page 1? Okay. So if we go here, just a reminder of what we did. We just used our limit definition for the function sign of the derivative. So we just inputted x plus h and x. And then from there, we did as much algebra as we could to try to simplify this expression. Okay, so the first thing we did is we applied the addition rule. There you go. And then from there, we were able to see that there was a common factor of sine x between the first and third term. So I just factored that out between the first and third term. And then I still had this middle term left over. And then from there, there wasn't much algebra we could do. So what we did is we tried to split up the limit as much as we could into simpler limits. Okay? So first of all, I just divided the h to both sides. I wrote it out so that all the expressions containing h were together. And then I considered the idea of splitting it up into simpler limits. You'll notice there's no limit in front of sine x and cos x. That's because they don't depend on h. All right? So they act like constants as h approaches 0. They don't change. But the only way for me to split this up into these simpler components is if both these limits exist. So that's what we talked about earlier. Okay? And what we showed was that it made sense that the limit for this sine h over h should be equal to 1, and that the limit of cos h minus 1 over h should be equal to 0, which then gave us a final result that the derivative should be cos x, which we confirmed by looking at it graphically. So we took the graph of sine x and we tried to draw the derivative function as best we could, and we even tried to be a little more precise. We actually drew a tangent line at 0 and realized that this tangent line, which is the steepest of all the tangent lines, had a slope of 1. So we knew that this function would go up to 1 and then down to -1 and back up to 0 and then back up to 1. And this is where we realized that, yeah, it made perfect sense that our derivative should be equal to cos x. Okay, is that okay, Sydney? Any other questions on that? Anything but how you apply the addition. Okay, so if you could tell me in what line Sydney, if you could just tell me, so let's call this line 1, 2, 3, 4, 5, 6. Okay, second line here. Okay, so here what I just did is I applied the addition rule for sine of a plus b. Okay, so sine of a plus b is sine of the first, so sine of a, so sine x, times cosine of b, which is h, so cos h, plus sine of the second, so sine h, times cosine of the first, which is x. So that's where this cos x came from. Okay, okay, good. You got that? Okay, any other questions? Yeah, it's still a thing, even though we're in calculus. Matthew, I guess the next live stream will be when I'm in New York for Model UN, and we're going to have to continue on with the course. Okay, for those who are leaving, thank you very much. Anything else? No face cam, guys. That's not going to happen. Kaiser Epic's a little strong for what this was. Okay, so are we good? Last call for questions. All right, so it looks like there's no more questions, so I'm going to end off. I know a couple of you had sent some video requests, so I'll do them in a little bit. Okay, and again, folks, please get that homework sheet done tonight. Get it done. All right. We'll talk to you folks later. If you have any other questions, that's right, calculus doesn't take snow days. Start that, whoever uses Twitter. Okay, see you all later, folks. Bye-bye. See you later.